Lab 2. The force of drag is obviously a very important factor in describing the physics of a moving object on Earth. In resisting an object's forward motion, it does things such as keep the speed of an aircraft in check and saves parachuters' lives every day. In this lab, I wanted to understand the motion of a falling object, specifically examining the effect of the drag force on an object's motion. Thus, I decided to emulate a parachuter. I taped a dime to a long piece of paper which functioned as a streamer and observed its motion. I built two models of the object's movement based on Newton's second law, one that incorporated drag into the equation and one that didn't. In the end, the model that incorporated drag was a much better fit at predicting the object's motion future, although it was still imperfect, but more on the results later. First, let's review the physics. When our object, or parachute, drops through the air, two forces are applied. First is the obvious weight force, which occurs due to gravity. The other is the drag force, which is the force of the fluid in which the object is moving resisting an object's forward motion. As usual, we can use Newton's second law to calculate the change in velocity. If we assume that the weight force is the sole force acting on the falling object, F net is equal to the weight force, and the object will continually accelerate downward. This would not be a bad assumption if the object received little to no air resistance, and so we use this equation to formulate our first model. However, we know this is unlikely considering that parachutes don't constantly accelerate downwards. If we incorporate the drag force, we can rewrite Newton's second law as the following, which expands to this when change in time is small. This is because the weight force is equal to the following, and is proportional to the square of the velocity, but becomes this when the constants are combined into one constant b. What does this tell us about the object's motion over time? Evident from the equation, as velocity gets large, the drag force becomes more and more important until it equals the weight force in magnitude. Theoretically, at this point, the object should reach an equilibrium, then proceed at constant velocity, aka the terminal velocity. These equations are the basis for the rest of our two future models. But first, let's collect some empirical data to fit our models too. Using a program called Tracker, the motion of the falling object was captured and its distance over time data collected. This was done by charting the object's position at every frame on an arbitrary coordinate axis, with the negative y direction set as the object's downward direction. The two equations talked about above, with and without drag, were employed to create two models in Python. Although the code may seem complicated, it simply employed Newton's second law to update the velocity over some small delta t, and then used the derivative of Newton's second law to update position. The computer iterates through this calculation with the initial velocity and position given, charting position with time, and displaying the relative sizes of the force vectors acting on the objects in the y direction at a given time. Our first model predicts position only with the weight force, and thus states that the object will accelerate constantly in the downward direction. Fitting this model to our collected, we can see that the model does a pretty good job predicting position at the beginning, but very quickly loses accuracy towards the end, over-predicting the object's position at the end. Thus it would seem some force is acting in the opposite direction, as we predicted might be the case. We can look at the model employing the drag force next. It uses the same equations in the previous model, only includes the drag force as we stated in our theory discussion before. But how do we find the constant b? We can calibrate to find b by in a trial and error basis until the model's last point reaches our observed last point. We find b is equal to 0.000628, and voila! Our model now includes the drag force pushing in the positive y direction. Looking at the new model in comparison to the data, it is a much better fit, especially at the end and the beginning of the data. But then again, it still doesn't look quite right. In the middle of the data, the fit is pretty poor. Looking at the change in velocity versus time from our data, we can see that the velocity becomes constant just before 0.5 seconds in free fall. This indicates that the object is already at terminal velocity by this point. Thus we can update our model just one more time. We fit our drag model just over the course where velocity is changing and recalibrate b to equal to 0.000648. Then we fit the remainder of the data to a line, and we have a good model with high r-squared value and terminal velocity of negative 4.335 meters per second. This model, which employs the drag force, is the best prediction of the motion future. What if we had thrown the object downward? Again, it would reach the same terminal velocity. Our model shows that the object will speed up or slow down until the weight force is equal in magnitude to the drag force and velocity is equal to 0. All in all, this lab was a success. The drag force model, with some tweaking, accurately predicted the motion of the ball, and it was used to find terminal velocity of the object.